Residence times in global reservoirs are an important aspect of the hydrologic cycle, and the reason for that is because we're concerned about the amount of time that water might spend in any of the major global reservoirs that make up the hydrologic cycle on a global scale. The focus of residence times includes global storages and fluxes, which just means places where water resides and the rates at which water flows into and out of those areas, or those volumes, the relative volumes of storage, the flow-through rates, meaning the amount of time that an average drop of water might spend in that reservoir, and storage times. Here's some questions to keep in mind as we examine the question of residence times in global reservoirs. First of all, what control volume is appropriate to analyze the global hydrologic cycle? What are the major reservoirs? And based on estimated annual volumes and transfer rates, what are the average residence times in the major reservoirs? And could we adapt this approach to Hunter Creek? Well, first of all, let's look at the hydrologic cycle on a global scale. The hydrologic cycle on a global scale is one that is primarily motivated by transfers of energy from areas where energy is highly concentrated, for example the equators, to areas where energy is not so highly concentrated, and that would be the poles. Largely via transfer of energy through water. That could be evaporation. It also can be condensation. If we look at the control volume of a typical section of the Earth's surface, it looks something like this. We have the atmosphere, in which evaporated water circulates. We have the soil surface, from which water evaporates and onto which water actually precipitates as it condenses in the atmosphere. And we have the subsurface, in which water is actually stored but remains circulating as part of the hydrologic cycle. The important thing about this is that when we look at relative rates of transfer into those three major reservoirs, that would be the atmosphere, the soil surface, and below the soil surface, the transfer rates vary significantly as we go from one reservoir to the next. So the atmospheric reservoir is one that sees very rapid turnover. The processes of precipitation and evaporation move water into and out of the atmosphere very quickly. When we arrive at the Earth's surface, the amount of water, or the rates at which water are transferred from the Earth's surface, begin to decrease pretty significantly as well. Here we have water in the form of surface water flows, rivers, streams, water stored in surface water bodies like lakes and in the ocean. And when we go to the subsurface, the residence time for the average drop of water that makes it to the subsurface as part of the hydrologic cycle increases pretty significantly as water encounters more and more resistance in the media that it flows through. The processes are entirely different for water transfer in each of these three major compartments. So the hydrologic cycle is motivated primarily by gravity, solar energy, and sometimes chemical gradients. And the general principle is that water flows from areas of high energy to lower energy, whether it be by gravity, meaning that the force of gravity has the potential to pull water down toward a lower surface or a lower elevation, or solar energy, in which water is stored, or solar energy is stored in water and used to evaporate water to help it move from place to place in the atmosphere. Chemical gradients can be significant in some instances, but generally chemical gradients also operate on the same principle as gravity, which means that chemical gradients, where chemical gradients are high, we have water flowing in to, in essence, reduce the amount of energy that's associated with high concentrations of anything. Storages include lakes, rivers, streams, groundwater, biological reservoirs, for example, forests, people, animals, the atmosphere, and glaciers. So these are places where water has some significant residence time, even if it's relatively short, as in the atmosphere. And then we have interstorage flows, for example, evaporation and transpiration, precipitation, and infiltration and runoff. These are the processes that move water from one reservoir to another, or even within a single reservoir. Graphically then, storage and fluxes look like this. We may have evapotranspiration leaving the landscape here indicated by the red arrows. Here's a control volume. That's a slice of a piece of landscape. We have precipitation coming in, here indicated from the cloud as a blue arrow. We might have groundwater outflow from our control volume, here indicated by a red arrow in the subsurface, and surface water outflow, which would be exported water through pipelines and canals. On the other hand, we may also have water coming in through pipelines and canals, in addition to the precipitation, and flowing in as groundwater as well. Storages then, particularly on the surface, or include the reservoirs, say managed reservoirs, groundwater, stream channels, lakes, atmosphere, and even soils. These are the abiotic reservoirs. Biotic storages include plants and animals, which actually compose a very minor fraction of the total of water available on the surface of the earth. Average annual storages vary according to the particular reservoir. So if we start to divide the reservoirs into smaller pieces, the volume of water in the oceans is about 1.3 million kilometers cubed, makes up about 97% of the total water on the surface of the earth. The atmosphere has approximately 13,000 kilometers cubed, and that makes up about 0.001% of the total water on the surface of the earth. Water in land areas is about 37,800,000 kilometers cubed, which makes up about 2.8% of the water on the surface of the earth, and so on. And we can see that ice caps and glaciers make up about 2.14% of the total water on the surface of the earth. Groundwater, a source we depend on, makes up about 0.61% of the percentage of total water. The major types of movement then include precipitation, evaporation, stream discharge, infiltration, groundwater flow, runoff, and transpiration and evaporation by plants. Approximate residence times for storages look like this. The residence time is proportional to the volume of storage divided by the flow rate. And that would be the net flow rate in and out. So the time, another way of expressing this is that T, or residence time, is equal to the volume, V, divided by Q, which would be the flow rate. Volume has the units of meters cubed, kilometers cubed, acre feet, any unit that really is a volume unit. And flow rate is expressed in units of volume per unit time. So it could be meters cubed per second, feet cubed per second, acre feet per day, or acre feet per year. Here's some example residence times. In the oceans, the volume is 1.3 times 10 to the 9th kilometers cubed. The discharge rate, primarily through evaporation from the ocean surface, is estimated to be about 505,000 kilometers cubed per year. So if we take our volume, 1.3 times 10 to the 9th, and we divide it by our discharge rate, which is 505 times 10 cubed kilometers cubed per year, we find that just canceling units and putting the units in the appropriate places, that the average residence time for a drop of water in the ocean is 2.5 times 10 to the third years, or about 2,500 years. On the land surface, using the reservoir, or the estimate of the amount of water stored on the landscape, the total volume is 116 times 10 cubed kilometers cubed per year. Our residence time on the land surface is about 100 years, the average residence time. You can see that groundwater is nearly double that, and the atmosphere has a very, very short turnaround time, much less than a year. So when we look at the rapidity of exchanges of volumes within these several sort of broad classifications of storages in the global hydrologic cycle, we see that the atmosphere is cycling through water through it much more quickly than the other three reservoirs depicted here, which would be the oceans, land, and groundwater. So let's look back at our questions. First of all, what control volume is appropriate to analyze the global hydrologic cycle? Well, based on the cross-section of the atmosphere that went all the way down to the subsoil surface, the control volume that would be appropriate for analyzing the global hydrologic cycle would be the entire Earth, plus the layer of the atmosphere in which most of the water vapor, or which all the water vapor exchange is taking place with the next compartments, which would include the ocean and the land surface. So the entire globe plus the atmosphere in which water is actively being transferred. The major reservoirs include the atmosphere, where rapid transfer takes place, the land surface, where exchange takes place between not only the atmosphere but also the subsurface, the oceans, which are again part of the Earth's surface, but slightly different because of the mass of water that's included there, and also the fairly rapid or the relatively slow turnaround time within those reservoirs, or in that reservoir, and groundwater. So based on estimated annual volumes and transfer rates, what are the average residence times of water in the major reservoirs? They include about 2,300 years in the ocean. Again, we're looking at a typical drop of water. For groundwater, which is faster than the oceans but slower than the two remaining reservoirs, we're talking about 240 years of residence time. On the land surface, we're talking about a century, and in the atmosphere, substantially less than 1 year. Would this approach work in Hunter Creek? Yes. It's a question of A, identifying the boundaries of the control volume. Where is the control volume for Hunter Creek? Is it the watershed boundary? Does the watershed boundary go to the subsurface? What assumptions what might we make to make it so that we can only isolate our analysis on a couple of different spots? Does the analysis actually consider the atmosphere? We can make assumptions about that as well, but when we establish a control volume, we have to understand not only what we're encasing in that control volume, we also have to understand how we're going to get measurements that represent inflows and outflows, and on what time step we need to carry out that analysis.